Hello everyone, welcome back to Chemical Engineering and Aspen channel. As you know, these days we are focusing on the subject of heat transfer operations. So in this regard, we are bringing the lecture number 4 for our valuable viewers. In our previous 3 lectures, we have covered the initial basics of heat transfer, the difference of heat transfer and thermodynamics, the driving force of heat transfer, the modes of heat transfer, including conduction, convection, radiation. Then we shifted our attention to the conduction. We have studied the Fourier's law of heat conduction in our previous lecture. And in today's lecture, we will solve an example related to the Fourier's law. Then we will move today to an important concept in the Fourier's law, which is the thermal conductivity. We will see what is the thermal conductivity, we will define it, how we can measure it, and then we will have final conclusion of today's lecture. So if you have not subscribed to the channel yet, please subscribe to the channel. Click on the bell icon to get all updates related to this channel. So let's solve an example, and the example statement is the roof of an electrically heated home is 6 meter long. As you can see this example, this figure as well, that it is 6 meter long, 8 meter wide, and the thickness is 0.25 meter and is made of a flat layer of concrete, the thermal conductivity of which is 0.8 watt per meter per Kelvin. The temperatures of the inner side, which is this one, is 15 degrees centigrade, while that of the outer side is 4 degrees centigrade for a period of 10 hours on one night. We have to determine the two parameters. Number one is the rate of heat loss through the roof that night, because there is no insulation here. So obviously heat will be lost from the system or from the roof. Number two, the cost of that heat loss to the homeowner if the cost of electricity is $0.08 per kilowatt hour. So basically there is no insulation. The inner temperature is 15 degrees centigrade, outer side temperature is 4 degrees centigrade, and the dimensions are given to us, the value of thermal conductivity is given to us. So we will apply the Fourier's law concept to calculate the heat loss, and then we will convert it in terms of the dollars as well. So we will assume the steady state conditions which exist during the entire night, because otherwise if we count in the unsteady state, the time dependency, the equations will be a bit complex and it will change, but we may do it at some later stages. And we will assume the constant properties which can be used for the roof, like that of the thermal conductivity, which was mentioned as 0.8 watt per meter Kelvin. So first thing is to calculate the rate of heat loss. We know the equation Q is equal to Ka dt over dx, and that dt is equal to T1 minus T2, and dx is the L, which is the thickness. So we know the value of K, which is 0.8 watt per meter Kelvin. We know the area how? By multiplying this 8 with 6, the length with the width. We know the inlet temperature or the inner surface temperature as 15 degrees centigrade. The outer temperature is 4 degrees centigrade. The L is 0.25 meters. Accordingly, substituting the values, and the total heat loss is 1690 watt or 1.69 kilowatt. So the total heat loss from this roof is 1.69 kilowatt. Going to the part B, which is the cost of heat loss to the homeowner. First, we will calculate the amount of energy. So how we can calculate that how much amount of energy is wasted in these 10 hours. So that can be achieved by multiplying the Q with the time. 1.69 multiplied by 10 hours gives you an answer of 16.9 kilowatt hour. And then cost can be calculated as amount of energy into unit cost of energy. So accordingly, 16.9 kilowatt hour into $0.08 per kilowatt hour. This kilowatt hour cancels with this kilowatt hour. So accordingly, the total cost or the total loss of the total cost or the total loss to the homeowner will be $1.35 for these 10 hours. If I go to the conclusion, the cost to the homeowner of the heat loss through the roof that night was $1.35. And let me say that this was just through the roof. We have not counted it through the walls. So accordingly, we have just counted this much region for the heat loss. But if we can include this loss, then the total loss will be higher. So how we can avoid it? We can use some insulations to protect this heat loss. So this was the first aspect of our today's lecture, that we have applied Fourier's law to calculate the heat loss, and we have converted it in terms of the dollars. Going to the second part, which is the thermal conductivity, and we will first start it today. We have seen that the different materials store heat differently, and we have defined the value Cp for its specific heat capacity. You have already studied about Cp. More the Cp, more will be the heat capacity, or more will be the storage. For example, for water, the value of Cp is 4.18, while for iron, it is 0.45 kilojoule per kg degree centigrade. That shows that water has higher storage capacity than that of the iron per unit mass. However, thermal conductivity is an opposite of it, but the concept is same, that thermal conductivity is related to the heat transmission, or the material ability to conduct heat. For example, if we say K is equal to 0.607 for water and for 80.2 watt per meter Kelvin for iron, it means that the iron conducts heat 100 times faster or 100 times more than water can. So the storage capacity of water is higher than iron, but the ability to transfer heat for iron is more than the water. So the Cp and K, you can say these are the opposite things. But the scenario is same: higher the value, higher the storage capacity in case of Cp, while higher the thermal ability or ability to conduct heat in case of the K. So we can define thermal conductivity as the rate of heat transfer through a unit thickness of material per unit area per unit temperature difference. High value means good conductor, low value means poor heat conductor. If we say K is equal to 401 watt per meter per Kelvin, that means that 1 meter thick copper wall will conduct heat at a rate of 401 watt per square meter area per Kelvin difference temperature across the wall. So this is how we define the thermal conductivity. And on this point, I will close the lecture, because first you need to understand what is thermal conductivity. The measurement of thermal conductivity will be dealt in our upcoming lecture. So I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.